History taught you that Vikings were warriors. It forgot to mention they were also metallurgists, the same craftsmen who forged the iron rivets holding the Gokstad ship together, excavated by archaeologist Nicolai Nicolaisen in 1882, and now housed at the Viking Ship Museum in Oslo, were running a surface treatment process on their iron and steel that the modern industrial rust prevention industry did not formally replicate until well after 1906. They had no chemistry lab, no spectrometer, no university. What they had was 4 generations of observing what happened to metal treated one specific way versus metal treated the wrong way. That observation was written into the hands of every blacksmith who trained under them. Passed forward in practice, not paper. The iron those craftsmen treated is still physically intact today, more than 1,100 years in the ground, in salt air, in cold museum storage, and the surface chemistry still holds. Replicating that process costs exactly $2. There is one specific thing Norse smiths did after the blade came out of the quench, not before, not during, that separated iron, lasting a decade from iron lasting centuries. It was not the alloy. It was not the forge temperature. It was one step that took under 5 minutes. That step is coming in a moment. First, understand what you're actually up against, because the industry currently selling you the alternative has been running that business for 120 years. The global corrosion protection coatings market, covering every rust prevention spray, wax treatment, and proprietary oil sold to households, workshops, and industrial buyers, was valued at over $22 billion in 2021, according to industry analysis published by Grand View Research. Petroleum-based sprays, proprietary blade oils, scheduled replacement kits, subscription sharpening programs that mail you a new treated blade and ask you not to ask why the old one stopped working. Every single product in that market solves a problem that was already solved. Viking crews did not get to test their solutions in comfortable conditions. Every technique they used was stress-tested by open ocean salt air, by freeze and thaw cycles in Greenlandic harbors, by bilge water sitting against iron hull fittings for months without drainage. If the metal failed, the ship failed, not struggled, failed. The iron rivets recovered from the Gokstad ship did not just survive a sea voyage. They survived 11 centuries of burial, salt, pressure, and exposure, and they are still structurally examinable at the Viking Ship Museum in Oslo, where conservators documented their surface condition in a 2001 report compiled by museum director Knut Berg. The copper fittings, pulled from the Birka trading post, documented by Hjalmar Stolpe across his excavations between 1871 and 1895, with findings held at the Swedish History Museum in Stockholm, tell the same story, not corroded to dust, intact, functional in form if not in use. They did not survive because someone preserved them carefully. They survived because the physics does not expire. The modern industry does not sell you a better outcome than the one those smiths produced. It sells you a recurring product where a one-time treatment cannot be invoiced. Here's the part the industry hoped you would never connect. Exactly how Norse smiths achieved that result and what the documented chemistry actually was. That answer is about 30 seconds away. This is not a new idea. Archaeometallurgist Alan Williams analyzed dozens of Viking Age and early medieval blades in his 2003 publication, The Knight and the Blast Furnace, published by Cambridge University Press. Williams documented that high-quality Norse blades showed evidence of controlled surface treatment distinct from simple quenching, surface carbon distribution patterns consistent with organic compound application at elevated temperature. His findings were cross-referenced against metallurgical examination of the Ulfbert swords, a class of Viking Age blades dated between 850 and 1050 CE, recognized by the distinctive inscribed mark found on examples held at the Germanisches National Museum in Nuremberg. The monk Theophilus wrote De Diversis Artibus around 1120 CE, a technical manual covering metalworking in practical detail, overlapping directly with the final decades of the Viking Age. In the section covering the hardening and finishing of iron, Theophilus explicitly describes the use of organic compounds applied during and after heat treatment to change the surface properties of the metal. The manuscript is preserved at the Biblioteca Medicea Laurentiana in Florence and was translated and analyzed by metallurgical historian C.R. Dodwell in a 1961 edition published by Thomas Nelson. Janet Lang and Barry Ager published their radiographic study of Viking Age and Anglo-Saxon swords from the British Museum's collection in 1989. Their analysis documented surface layering on intact blades consistent with deliberate post-forge organic treatment. Not accidental preservation, but structured application that altered the outermost iron structure in ways still measurable nearly 12 centuries later. The result was a blade that did not just stay sharp, it stayed. Full stop. That result was not difficult to achieve. It was a commercial inconvenience. In the 1880s and 1890s, the first industrial rust prevention coatings entered the European and American market. Petroleum-based compounds, mineral oil emulsions, early cosmoline-type greases developed for long-term metal storage. These required ongoing supply from a manufacturer. They required replacement on a schedule. They required purchasing from someone. Raw linseed oil and a fire require purchasing from no one. Not wrong, inconvenient. The Norse blacksmith tradition that passed this treatment hand to hand for 3 centuries, documented in the material record of Birka, Hedeby, and the smithing sites of the Trondheim region excavated by Norwegian archaeologist Asbjørn Hertag across the 1950s and 1960s, and published in his 1969 report, Contributions to the Medieval History of Bergen, held at the University of Bergen, did not become worthless because a better product replaced it. It became worthless because a billable product needed room to exist. You cannot sell a subscription to a linseed oil application. You can sell one to a proprietary coating on a 12-month replacement cycle. The billing cycle simply did not have room for free. At the height of the Norse trading network, every crew running the Volga route from Novgorod to Baghdad, documented in eyewitness detail by Ibn Fadlan in his 921 CE account known as the Risala, preserved at the Meshid Shrine Library in Iran, and translated by historian Richard Fry in 2005, carried iron blades, tools, and fittings treated this way. Every single one of those crews crossed environments that destroy untreated iron in weeks. Salt air on the Baltic, acidic freshwater on the river systems, the condensation of cold nights sitting against bare metal with nowhere to drain. They crossed all of it without a maintenance schedule, without a replacement product, without a supplier anywhere along the route. The average household today spends between $40 and $90 a year on rust prevention, blade oil, and protective coating products for knives, tools, and outdoor equipment. Norse crews covering thousands of miles of open water and river systems spent nothing. The chemistry they used has not changed by a single variable since the year 900 CE. It is in your kitchen right now, and almost nobody is using it. If that stopped you, this channel exists for exactly that reason. Every week we recover one more technique the industry assumed you would never find. Subscribe and hit the bell so you do not miss the next one. You have seen this your whole life and never connected the dots. When you season a cast iron pan, when you rub oil into it, put it on high heat, and watch it smoke until it turns dark, you are doing what Norse smiths did to their blades. You are forcing a thin layer of polymerized oil into a hot iron surface. It bonds, it seals. It does not come off with water. When you oil a wooden cutting board after washing it, you are applying the same thinking to a different material. Oil fills the small gaps. Heat drives it deeper. The result is a surface water cannot penetrate. The Norse blacksmith was doing both of those things at once. To iron. The logic is simple. The result is hard to argue with. Most people who try to replicate this get the first step wrong. Not the oil, the temperature. Getting that one detail right is the difference between a surface that holds for a century and one that peels off in a season. Here is everything you need. Here is what you need, and I want to be honest with you about every number. Raw linseed oil, not boiled, not blended. Raw. A small bottle, enough to treat 10 to 15 blades, costs around $2 at any hardware store or farm supply. It is the same material farmers have used on metal tools for generations, a piece of clean cotton cloth. You already own this. An old t-shirt cut into a palm-sized square works perfectly. A heat source, a kitchen stove burner, a propane torch, or a forge if you have one. You do not need a forge. The stove works. Your blade, tool, or iron object. This works on kitchen knives, garden tools, axes, chisels, any bare iron or carbon steel. It does not work on stainless steel. Stainless already has a chromium oxide barrier built into its surface chemistry. That is a separate technique in a separate video. Tongs or oven mitts. The metal will be hot enough to burn skin immediately. That is genuinely it. Here's the one thing most people get wrong when they try to do what Norse smiths did. They apply the oil to cold metal. It does not work on cold metal. Not because cold iron rejects oil, it absorbs it, but oil on cold metal sits on the surface the way water sits on a cold pan. It does not bond. Within a week, it has gone gummy, collected dust, and begun trapping moisture underneath it. That is worse than no treatment at all. Every Norse crew that lost tools to rust on a long voyage, documented in the ship inventory analysis compiled by Ole Crumlin Pedersen at the Viking Ship Museum in Roskilde and published in Ships and Boats of the North, Volume 4, in 2002, lost them to this exact failure. Cold application. The oil sat on top. The salt air found its way beneath. The crews whose iron survived, the Gokstad ship's iron fittings, still structurally sound after 11 centuries, applied oil to hot metal. Specifically, metal hot enough to make the oil smoke the instant it makes contact. Not burning. Smoking. That temperature is what creates the bond. Here is why that works. When iron heats up, its surface forms a thin layer of iron oxide. Picture the way a cast iron pan turns a slightly gray-blue color when it gets truly hot on the stove. That layer is porous at the microscopic level, like a sponge with openings too small to see but large enough to matter. When raw linseed oil touches that hot, porous layer, the heat breaks the oil down into smaller molecular chains. Those chains flow into the pores, then they polymerize. They lock together inside the metal's surface the way resin hardens inside wood grain when it cures. What forms is not a coating on top of the metal. It is oil in the metal, locked in, cured in place. Water molecules cannot get past it. Oxygen cannot push through it. The rust cycle cannot begin because the surface condition the rust cycle requires no longer exists. Heat your blade evenly over your stove or torch. Move it slowly through the heat. You're not going for red hot. That is forging temperature, which is far beyond what you need here. You are looking for a temperature range old smiths called the straw to blue zone. No thermometer required. Hold the blade over the heat and watch the flat surface. It will shift from its usual gray to a pale gold, then to a deeper straw yellow, then to a blue purple. The moment you see that first blue tinge appear, pull the blade from the heat. That blue color is the signal. It tells you the iron oxide layer has formed, is active, and is ready to receive the oil. What you do in the next 30 seconds determines whether this treatment holds for 10 years or 100. Most people move too fast here and miss it entirely. And the reason that timing matters is the difference between locking the oil into an active surface and painting it onto a surface that has already sealed itself. One step is coming up that makes this exact moment make sense. Wait for the blue. Pull immediately. The window is about 30 seconds before the surface thickens past the useful range. Dip your cloth into the raw linseed oil. Use less than you think you need. A coin-sized amount on the cloth is enough for one side of a blade. Wipe it onto the hot surface in one smooth stroke. Watch for smoke. Thin, white smoke rising the instant oil meets metal. That smoke is the chemistry happening. If there is no smoke, the metal is not hot enough. Reheat and try again. If the oil catches a yellow flame, the metal is too hot. Now let it cool slightly, then continue. After the first coat, reheat gently and apply a second pass. 2 coats fills any gaps from the first. 2 coats is enough. Set the blade in still air and let it cool completely. Do not rush this. Do not quench it. The surface, when cool, will be dark, somewhere between deep amber and near black, depending on your steel. It will feel dry to the touch, not greasy, not slick, dry and sealed. Now here is the only test you need. Run water over the treated surface, not a quick rinse. Hold it under a running tap for 30 full seconds. Then hold the blade up and watch. The water will bead up and roll off. It will not sit flat on the surface. It will not absorb. Water beating on metal tells you the polymerized layer is complete and continuous. If water sits flat on any section, that spot needs one more heat and oil pass. That is the entire test. No equipment, no chemicals, no pH strips, just water. The complete Norse maritime tradition was built on tests exactly this simple. A check you could run in a ship's hold, in the dark, in salt air with cold hands, in the middle of the North Atlantic. What you just built is one of dozens of Norse techniques this channel covers. Every single one was set aside for the same reason. It could not be invoiced. If that matters to you, subscribe. This is where that knowledge lives. One blade treated this way protects one blade. What Norse settlements did with this same process at full scale is the part that changes how you think about the cost entirely, because the numbers at community scale are where the real argument against the modern industry sits in plain sight. A Norse settlement comparable to Hedeby at its operational peak, Hedeby's population estimated by archaeologist Elsa Rosedal in The Vikings, published by Penguin in 1987, at roughly 1,000 to 1,500 residents during its prime from 800 to 1050 CE, maintained hundreds of iron tools, blades, structural fittings, and fasteners using this exact process with essentially no supply chain and no external vendor. 1 unit of raw linseed oil, a quantity costing roughly $8 at full retail today, treats 15 to 20 pieces of iron. A community of that size, treating its entire metal stock for a season, required a supply that any settlement with access to flax could produce entirely from its own land. Think about what that means for a single household. 1 bottle of linseed oil treats every knife, every garden tool, every axe, every cast iron pan you own. It does not expire. It does not require a refill. It does not need to be purchased again until it runs out. And for a household of 4 treating its tools once a year, that could take 2 years or more. No bills, no infrastructure, no asking anyone's permission. There is one condition where this technique performs less well than in all others. Norse craftsmen knew it. They accounted for it. The way they solved it is the last thing in this script. Stagnant fresh water. Specifically, water sitting still with high organic content. Swamp edges, river backwater, standing pools rich with decomposing matter. Salt water corrodes most metals faster than fresh water under ordinary conditions. But this particular kind of acidic fresh water works differently. Salt pulls moisture toward the metal surface through osmosis. Acidic fresh water softens the outer polymerized oil layer over time, creating microscopic pathways for oxygen to reach the iron underneath. The linseed treatment resists salt air well. It resists acidic standing water less effectively. Blades stored in those conditions, in vessels that spent extended time on river systems, specifically the eastern Volga and Dnieper routes used by Rus Vikings, showed degraded surface treatment in the artifact record recovered from the Gnezdovo burial complex near Smolensk. Those findings were analyzed by archaeologist Tamara Pushkina and published in her 1996 report on Norse material culture in the Upper Volga region, held at Moscow State University. The Norse solution was simple and required nothing new. First, reapplication. A light heat and oil pass after any extended freshwater exposure. Not a full refinish, a maintenance coat, 10 minutes at a fire. This restored the surface chemistry before degradation reached the iron. Second, rendered tallow, beef or mutton fat boiled down to a clear liquid, applied as a base layer under the linseed oil on blades expected to see river use. Tallow creates a slightly thicker, softer barrier that resists acidic water better than the oil layer alone. The combination of tallow base and linseed top coat was the Norse answer to the one condition their standard treatment handled least well. Rendered tallow from beef fat costs less than $1. The fix for the technique's single weakness costs $1. The iron rivets from the Gokstad ship are still in Oslo. They are not behind protective glass because they are fragile. They are behind glass because they are 11 centuries old and still structurally sound. And that combination is what makes them worth protecting. The surface treatment on those rivets still holds. The chemistry still operates. The oxide layer, bonded with organic oil sometime around the year 900 CE, is still performing the exact function it was applied to perform. The physics does not care that it is old. The raw linseed oil in your hardware store is the same molecular structure as what Norse smiths applied to hot iron in the 9th century. The iron oxide layer on your blade forms the same way theirs did. The polymerization happens the same way. The water still beads. What you built today does the same thing. I do not know what brought you here. It does not matter. It works either way.